So today is actually going to be very little of me talking and mostly you problem solving and me circulating around and offering my assistance when needed. Okay? If you guys would, I hope you have your notes from last class because that's going to be helpful. I want you to have that long titration problem that we did. Have that in front of you. That wasn't the very last thing that we did, but it was a 5-step titration problem. Okay, and I want you to have that in front of you because I want to just kind of summarize it. I know we've already looked at this graph, but I want to just look at it one more time. Okay, if we had been plotting the pHs as we were going through that problem, if we'd been plotting them on a graph, we would have gotten some kind of a curve shaped, something like that. Okay, so if you would, guys, in that 5-step problem we did, look at the very first step. So in your notes, it probably says like 0 milliliters. Okay. All we had at that very first step was a weak acid and nothing else. Or we had water, but okay. Look at how you did that calculation. What kind of ice table did you use to solve that first step? It was a Womix, okay? The next 2 steps are in this range. Anywhere after 0 and before the equivalence point, we've started adding base. We had what I call Newman ice tables. But look at your problem. The next 2 calculations, what were we left with at the end of those Newman ice tables? Buffer systems. And what do you use to help you calculate the pH? Hendy-Haas. Okay. So you're left with a buffer, which means you can use Hendy-Haas. I'm going to call it HH. Now, they have this area bracketed, but really it's anywhere before the equivalence point. Okay. They've got the equivalence point marked at 50, which means the halfway point is where? What's half of 50? Okay, 25, so that's a point like right there. Look at your notes. What is special about the pH at the halfway point? pKa. Very good. Okay. All right. Look at the second to last calculation, which was at the equivalence point. Let's review. What does it mean to be at equivalence? What's equal? Moles of acid equal moles of base. Okay. Look at what you did for this calculation. We first did a Newman, and then at the end of that Newman ice table, what were you left with? It wasn't a buffer. Just one thing. And in this particular problem, that one thing was a weak base. And then what did you do next? We did a Womix with that weak base in this case. And this was the point in the calculation that got really long and frustrating and takes a lot of work. Okay? Anywhere beyond the equivalence point, now they've highlighted just this region, but really it's anywhere after the equivalence point. Look at your last calculation. We did a Newman. What were you left with at the end? It's not a buffer. It's not one thing. It was 2 bases, 2 of the same thing. And how did you know which one to go with? We went with the stronger. 2 of the same thing. And you chose correctly to look at just the stronger one. Okay. So if you look at this, guys, anytime you're doing a titration, there's basically 3 situations you could come across. You do a Newman ice table. At the end, you might have a buffer. And if you do, you Hendy-Haas it. Situation 2, you might be left with just one thing left over, which means you're at the equivalence point, you Wommax it. Third and final situation, at the end of your Newman ice table, you're left with 2 of the same type of thing. You don't have to deal with both of them, you just focus on the stronger one. Somebody yesterday asked me a great question. When you are supposed to go with the stronger one, you know, is there going to be a situation where I'm not sure which one is stronger? No, there isn't. Okay? Because, guys, one of these things is always going to be the King Daddy. It's either going to be H plus or it's going to be OH minus. It's not going to be some big mystery as to which is the stronger one. Okay? So, what we're going to do today, well, mostly you are going to do, and I'm going to help you. We're going to switch these 2 words right here. All right? This is your main task for today. All I have done is switch the words weak and strong. You guys are going to do this calculation on your own. Here is your goal. Okay? Yes, I'm going to do them with you. I'm going to put the answers up as we go. But your goal is to stay 1 step ahead of me. What I mean by that is when I put up the answer for this first addition of acid, you should be on to the next one already. I'm going to take my time. I'm going to give you some space to work through this. I'm going to circulate around and I will offer my help. Okay? All right, here is the first step. I'm hoping most of you are ahead of me. How'd you do on the first one, okay? Good. Keep working. Here's the next step. This is the second step. Now, guys, I want to say something about this buffer situation. Okay, at the end of this Newman ice table, I was left with a buffer, which means I can use Hendy-Haas. Now, a lot of you said, okay, well, this is a, kind of a basic situation, so I'm just going to change this to POH. Guys, you got to be careful. The equation is what it is. Okay, the way it is written on your equation sheet says pH equals pKa, and that's why I did this. I was not given a Ka, so I had to find it. Plus log of base over acid. Now, some of you were smart enough to figure out, and you don't have to do this, this is an option. You can take the Hendy-Haas equation and make everything the opposite. Instead of pH, make that POH. Instead of pKa, make it pKb. Plus log of, instead of base over acid, which is what we usually deal with, flip it, acid over base. If you make all 3 of these pieces the opposite, that is another form of the Hendy-Haas equation. It's not written on here, but you could use that if you want. I didn't. I chose to just go with the way it is on our equation sheet. I had to find Ka, but there it is. Okay, there's the third step. Look, it's pink. I know, right? Okay, there's the equivalence point. I tried to write it as neatly as I could. All right, and there's the last one. Well, and that's the thing, guys. As I said before, you know, would a test question have all 5 of these calculations on it? No, they wouldn't. I would focus in on maybe just this one part, okay? Which sounds much better, but actually it's a little bit more challenging because you don't know where you are. You don't know what to expect at the end of that Newman ice table because you haven't been going through a pattern yet. Okay? So, let's pull up a graph. If we had been keeping track of these points and plotting them as we went, we would get a curve that would look something like this. It's not a perfect reverse S, but it has that same general shape. Okay? They've told us that the equivalence point is at 50, which means the halfway point is where? At 25, so that's in all likelihood that data point right there. And just refresh my memory, guys, what is so special about the pH at the halfway point? It equals pKa. Right? So you could be asked to do calculations like you were on that previous slide. You might be asked to get some information off of a graph. Tell me this, anywhere in this region, let's see if you were listening at the beginning of class, anywhere in here, at the end of that Newman ice table, what are you left with? A buffer system. You use Hendehaas. At the end of the Newman ice table here, you're left with just one thing, and what do? You Womix it. Anywhere in here, what are you left with? 2 of the same thing. In this particular case, it was 2 acids. Which one do you go with? The stronger one. Okay, very good. Okay, so let's wrap up this acid-base section by talking about indicators. Now, I asked you to get a book. If you would, please, go to page 664. 664. Okay, now, guys, the entire purpose of doing a titration, which we will eventually do, we're going to do one in a couple of weeks. The purpose of a titration is that could be the acid, could be the base. There's something about either the acid or the base that we don't know. And usually it's either your acid or your base. We don't know the molarity of it. You do a titration to figure that out. And the place that you're always trying to get to is the equivalence point. When you do a titration, your goal is to titrate, to add acid or base, whatever you're doing, until you get to the equivalence point. Here's the problem. Most solutions out there are clear. Most acids are clear. Most bases are clear solutions. How do we know when we've gotten to the equivalence point? You add clear to clear, you just get more clear. We use what are called indicators to give us a visual clue. Like visual, we can see it with our eyes when we have reached the equivalence point. We use indicators. Indicators, guys, first of all, indicators are themselves weak acids. Okay, and if you're wondering, you know, does adding a weak acid to a titration, doesn't that like mess up the titration? Well, when we add indicators, guys, we're adding like drops, just drops of these indicators. We're not adding enough to make a difference, like to affect the pH. But here's what else is special about indicators. They are compounds that have color to them. And not just one color, but two. Okay? They are compounds that in their two different forms exist in two different colors. By the way, I'm using the letters IN here to mean indicator, not the element indium, by the way, just so we're clear. Okay? And what determines the color is that indicator in its acidic form or in its basic form? All right? For example, methyl red is an indicator that is red in its acidic form, yellow in its basic form. I want you to look at this equilibrium reaction and think Le Chatelier's principle. Like, you change something about the reaction, does it shift one way or not? Let's imagine that I add some methyl red, this situation, this equilibrium, to a beaker that contains hydrochloric acid. Strong or weak hydrochloric? Very strong. Lots of OH floating around or very little? Lots. Imagine in this equation, if I add lots and lots of H+, which way will this shift? That way. If I add a few drops of this methyl red indicator to something very, very acidic, it will be red in its color. If I were to add this indicator to something very, very basic, like lithium hydroxide solution, hydroxide isn't in this equation, but if you have something very, very basic, you can think of that as decreasing the amount of H+. Which way would this shift? To the right. So it would turn yellow. Okay? So we use indicators to tell us what's going on with the pH. The pH of the environment is what controls the color of your indicator. The pH of the environment is what controls this equilibrium. Okay? If you see this vocabulary term, endpoint, endpoint just means when the indicator changes color. Okay? If we're using an indicator in a titration, you can think of the term endpoint and equivalence point to mean the same thing. Okay? They don't exactly mean the same thing, but if we're doing a titration, the indicator will change color at the equivalence point. Okay? Now, can you use any indicator you want for any titration? No, you cannot. Here's where I want you to focus, is right here. If I am doing a titration, and as the titration goes on, the pH is going up, it's rising. What must I be adding more and more of? If the pH is rising, OH minus, I must be adding more and more base. Here's where an indicator will change color. If you're, the way we say it is, if you're titrating up in pH. pH of color change equals pKa minus 1. Now, wait a second. What are we even talking about here? Remember what I said. Indicators are themselves weak acids. Don't weak acids have Ka values? Nod your heads. Okay. I'm going to choose an indicator that we will use in our next lab. It has a very long name. Okay? When you say this word, in English, PH together has an F sound. Try putting an F and a TH sound together. Okay? Saying the name of this indicator actually works better if you have a lisp. Okay? Phenolphthalein. There's a lot of spitting involved. Okay, don't be close to anybody when you say that word. Phenolphthalein. All right? But that's the name of the indicator we're going to use. And I'm going to tell you its Ka value. This is not exactly what it is, but it's pretty close to this number. Okay. Weak acids are, indicators are weak acids themselves. Here is phenolphtalene's Ka value. Do not pick up your calculator. What is the pKa of this indicator? 9. Okay. What's 9 minus 1? 8. All right. God, you guys are good. You guys are good. Okay. So what does that even mean? That means this particular indicator, which goes from a clear color, which absence of color, however you think of it, to bright, bright, bright pink, magenta pink. Okay. When is that going to happen? Well, if we're titrating up, that will happen at a pH of 8. Well, what if you're titrating down? If you're titrating down, what must we be adding more and more and more of? H plus, acid. If we're titrating down, the color changes at pKa plus 1. What was our value for pKa again? What was it? 9? What's 9 plus 1? All right. 10. Here's the ultimate take-home message. This is what I want you to really get off of this slide. Every indicator has what's called a useful range. If the pKa of phenolphthalein is 9 plus or minus 1, that is a range of 8 to 10. Now, what does that even mean? That means phenolphthalein would be a good choice for an indicator. Listen carefully here. This is important. Phenolphthalein would be phenolphthalein would be a good choice for an indicator if the pH at equivalence is in this range. If pH at equivalence is outside of this range, then that's not a good choice for an indicator. I should choose a different one. Okay? Please look at this chart in your book. There are 7 different indicators. There's many more than what are in this chart, but just look at the ones they've given us. Each one has a band, which is not only showing you the colors that these indicators turn, but it's also showing you where their useful ranges are. Tell me, please, look at this chart. Which indicator would be a good choice for a strong acid, strong base titration? Well, let's review that. What's the pH at equivalence for strong? 7. Which one of these would be a good choice? Yeah, bromphimol blue. Here's a pH of 7. That would be a good choice. Okay. Look back at that very long problem that we just did today. Find the step in your calculations that is the equivalence point. Tell me, what was that pH? 5.21? What would be a good choice? Yeah, probably methyl red. Go back to the class even before that. Look at that other titration we did. Find the step that was the equivalence point. What was the pH for that one? 8.79. What do you think? We could use phenolphthalein. What else could we use? Probably thymol blue. Okay. Anybody want to guess why this one might have 2 useful ranges? I'll give you a hint. Remember, indicators are acids. What do acids do? What's their definition of an acid? Hydrogen ion donor. Each time hydrogen is donated, there's a useful range. Why might there be 2? What if it's a diprotic acid? There's more than one hydrogen to give. Okay. So some indicators have more than one useful range. Okay. The very last thing I want to do, guys, is a little, just very quick, practice multiple choice situation. Well, let me write down some answer choices. Okay. Let's say you're in multiple choice and you come across a question that says, which of the following could be the pH at equivalence for a titration involving this acid and this base? Why is the answer C? Strong acid, strong base. You're right. The answer is C. Okay. How about this? B as in boy or D as in duck? Look at the nature of these things being added. Strong acid, weak base. Who dominates? The acid. It's B. Now, the pH at equivalence should be in the acidic range. It's not A, because, yeah, that's in the acidic range, but guys, that is like really acidic, okay? Your pHs at equivalence are not going to be at the extreme ends of the scale. What if you had this? This one. How about that? D. Yeah. Weak acid, strong base. Okay. So the answer would be D. All right? Yeah, nitrous, weak acid, not nitric. Okay, guys? That's where we'll stop.